crap, my bad. I was just trying to catch some shut-eye and I realized I gotta record another math video. All right, guys, we're back talking about invertible maps. All right, and in the last video we showed that invertible maps are actually unique in that if you have a linear map and it has an inverse, you can't have more than one inverse, right? That inverse is unique. So now we're going to talk about how can we prove invertibility, because okay, we said all these yapperonis, all of this yap about like, okay, well, if we have an inverse, this is true. How do we actually go about showing, that a function's invertible? And so that's what we're going to talk about here. And what I want to show is that, okay, so we have some linear map T, just the U's from V to W, right? Well, when is T invertible? So T is invertible if and only if the following two things hold. Okay, well, before we just give you the answer, because unfortunately I have to break it to you guys that I'm not Mr. Nice Guy. I gotta make you work, for this knowledge that I'm bestowing you guys upon. So I'm gonna give you guys some hints, all right? Well, remember, if you look, oh my God, just kidding me. Okay, the sine of x is what I'm trying to draw. All right, I just had to lock in. Sine of x. Remember the last video? If you didn't watch the last video, go watch the last video, okay? But if you remember sine of x, why wasn't it invertible? Because we had all this nonsense with like having multiple points on the same y level. Because again, when you swap the y and the x, which is what happens when you take the inverse, they become these 2 points, right? Become this, right? They go on the vertical axis. So now we have 2 points on the same x value, and that's not a function, right? You know how functions, they only map 1 point to another point. They can't map 1 point to 2 points. So this can't work, right? And so what does this mean? Well, this is the same thing as being 1-to-1, right? I hope you guys guessed that. All right, being 1-to-1 means that we only map 1 point to a different point. Let me rephrase that. What am I saying? For every point that you map to the codomain, right? If you have 2 different points in the domain, you have to map to 2 different points in the codomain. Like, they can't be the same. You can't be mapping like, what is this, 0 and pi over 2 to 0. Like, these are being mapped to the same thing. We don't want that, all right? Okay, well, okay, is that enough to be invertible? Well, I claim it's not. The thing is, what's interesting and what I'm also going to show is that this is enough to be invertible if your linear map is actually an operator, meaning it's going from the same space to the same space. So one space to the same space, or going from one space of one dimension to another space of the same dimension. Okay, I'm saying a lot of words, but we'll get to that. And so we're getting close. Okay. Well, the thing is, what we've taken for granted with sine is that sine can cover, maybe sine isn't the best example. Let's try another example. Let's look at like, maybe this isn't the best example, but it's the best I can think of for now. So x cubed, right? Wonky looking x cubed. X cubed eventually covers all y values, right? It's surjective, right? It means that eventually, again, we're mapping from R to R, so we eventually cover all R values, right? Whereas, for example, like the parabola, it only covers positive real numbers, okay? And why is x cubed invertible and x squared not invertible? Well, first of all, this doesn't pass this kind of test. This isn't 1-to-1, right? But even still, like, this is important that it's surjective, right? What happens if it's not surjective? That means that once you swap the x and the y values, your like domain. So for example, let's say instead of looking at x cubed, if we got rid of this part, all right, so this is clearly 1-to-1. This is like half, let's say this is like half of the y equals x squared. All right, so this half. This is 1 to 1. We agree this is injective. But once you swap the x and the y values, suddenly your domain is incomplete. Okay, so you're literally mapping from one domain to another domain. But one domain, like you can't, like some of the points in your domain don't map to things in your codomain. So you're essentially lying about what your domain is. Okay, so that's why we need that surjectivity. Again, all that deal with swapping the x and the y values. Okay. So in summary, this is true if and only if T is injective and surjective. Okay, fancy schmancy words, right? I always feel like I sound really smart when I'm saying that, but like everyone knows what this means. Okay, it's just words. It's an alphabet soup. Anyhow, can you even see my face? I swear, if I look at that video and see my face cut off while I'm standing here, I'm gonna cry. I really hope you can see my face. Injective, surjective. Okay, proof. Gee, this might be a long proof. But anyways, I promise you guys we're doing this, so it's okay. So, forward direction. Again, it's an if and only if. So we need to do both directions. And I'm thinking, do I leave one of the directions as an exercise to you guys? I don't know. I'm kind of feeling a little evil today. But which side is harder when we think about that? Injective. Let's just go for it. All right, we'll go with the flow. Okay, so the forward direction, yada yada. So we're assuming, so assume T invertible, right? Okay. Well, let's start with injective. Let's try proving that. All right, we got to start with something. So injective, organize a little bit. So injective, well, okay. To be injective, if two things, so let's take x and y in our vector space V, our domain, and we want to show that f of x, or let's take x not equal to y, okay? Then we want to show that f of x is not equal to f of y, okay? That's one way we could do it. Actually, maybe it's easier, we take the contrapositive of that, because usually how it's stated is if your outputs, why am I doing f, guys? Oh my goodness. So if t of x equals t of y, the only case where that holds is if your inputs are both equal. So if that implies x equals y, question mark. So that's a question mark. So we're gonna assume that this holds. So we're taking any arbitrary x and y, we're taking t of that, and we're assuming that those are equal, okay. Well, this is actually really easy because we can take the inverse of t on both sides. Boom. We're assuming t is invertible, we can do that. And again, these things cancel out in a nice way. It turns into the identity. So in particular, it's just x and y left. So this indeed implies x equals y. Really easy. Moving on to surjectivity. Okay, so we need to take some, let's say, y, again, we're using notation, ignore that, that has nothing to do with this. Some y in w, okay? Let's use w, little w in w, okay? We want to find like some v in v so that t of v equals w, right? That's what it means to be surjective. Okay. Well, remember, t of t inverse of w, that's just equal to w. That's like my first instinct. Well, what's inside here? What type of quantity is that? Again, t inverse goes from the codomain of t to the domain of t. So this is a quantity, this is in v, right? Because it's mapped into v. So we just choose this guy, right? Boom, this is equal to our v. So we found v so that t of v equals w. Simple. So that first direction, actually really easy. Should have left it to you guys. I regret everything. Okay, moving on. Let's knock this out. This direction might be a little more tricky, but we'll figure it out as we go. So, I don't even know if I know the proof to this. So we're gonna figure it out together. The more you know. This is beautiful. Doing math with my audience. I love it. Get rid of this. I don't like that guy. Okay. So the other direction, we assume T injective plus surjective. All right. Wonderful. T injective, surjective. How do we prove T is invertible? Okay, it's a little tricky. Well, we want to find some kind of function. Do we find a function? That's the question. So we want to find some function, right? So that, again, this goes from, let's say, again, it's from W to V, so that TS equals ST equals the identity. Okay. So we want to find a function like this. Well, let's think about it like this. If T is injective and surjective, right? For every, we're going to try to construct one. Again, this is kind of tricky, these constructive proofs. Okay, so for every, let's take any W in, let's say W, okay? Because we're trying to construct T inverse, right? So we need to find a V that we want to map this guy to. We want to find something inside of that vector space V that we want to map any W to. Okay, now I have an idea. Well, we know since T is surjective that there exists some, let's say V in V, so that, again, I'm just stating the definition of surjectivity, so that yes, so that T of V is equal to W. Okay, great. So we have this. Now, what if we map W to V? Does that define a well-defined map? That's the question. Because that's, I mean, what if we have like, is this a unique V? That's the question. What if there's another, let's say, X? Does there exist another T of X so that T of X equals W? We need to check this so that it's well defined, because again, function can only map to one other output. It can't map to do two different things. Okay, well, assume this is true. So if T of X equals T of W, okay, well, that means we can set these two equal. So T of V equals T of X. Oh wait, T is injective. Okay, that's very convenient. This means V equals X. Great. So this means that it is indeed well defined. The thing that we want to map W to, it has to be unique, right? We can't think of two different things to do that. Okay, so that's going to be our function. We're going to choose T inverse to be basically constructed like this, where we take any W in W, and then we find the V using that surjectivity that maps uniquely to that W, and boom. Now, does this satisfy? All right, I'm going to say S. I'm going to call that S, okay? Does this satisfy our requirement for invertibility? Well, let's see. If let's take any, and I think what we've done here, it basically follows directly from that, but let's check. So let's take any, let's say, W in W. Again, we're using notation, sorry guys. That's how it's got to be. W in W, then again, and this is how we constructed V. So T inverse, or sorry, S of V. Well, what's that? That's just, again, V, S of V. We got to figure out our notation properly. So S of V, or S of W, is equal to V, where V is so that T of V equals W. Okay, so let's take T on both sides, right? So TS, okay, T of V, what's T of V? T of V is W, okay. Okay, so TS of W equals W. Great, we have that identity property. We're mapping W to itself. whenever we compose T and S. Now, the same thing you can do to show S of T of, well, in this case, actually, T of V equals V. So I'll let you guys try that, okay? You just try that, because I've done all the work. I need to spread the labor a little bit, all right? I'm 18 now, so I'm an unk, right? My back is aching. You guys gotta cut me some slack, all right? So I'll leave it to you youngins to figure this out. But in any case, I'll catch you guys in the flip. In the next video, I'm probably gonna be talking about, well, what happens if we work from one vector space with the same dimension to another vector space with that same dimension, okay? We get an interesting thing, which is that we can actually remove one of these requirements and we still get invertibility. So we'll prove that in the next one. And then we're gonna talk about, probably then we're gonna talk about my favorite topic, eigenvectors, eigenvalues, all that cool jazz. So hats off to you, my fellows. See you guys in the next video.